Welcome to Lecture Online. In the previous video, we explained what the Lagrangian equation is and how it actually works, but we didn't know why it works. You look at this equation and go, how can this tell you the equations of motion of any situation? Well, let's go back to the beginning. The Lagrangian is defined as the difference between the kinetic energy and the potential energy of an object. In this case, we use a simple example, the free fall of an object towards the ground. Also, we can say that the kinetic energy, which can be defined as 1/2 mv squared, can be written in generalized coordinates as 1/2 m times x dot squared. Remember that x dot simply means dx dt, the first derivative of x with respect to time, which is velocity. X double dot means the second derivative of x with respect to time, which means acceleration. The potential energy, which is mgy, can then be written in generalized coordinates as mgx. Now, the Lagrangian is simply the difference between those two. We can say the Lagrangian is equal to the kinetic energy minus the potential energy, which is equal to 1/2 mx dot squared, that's the kinetic energy, minus mgx, which is the potential energy, again in generalized coordinates. Now, the question was, why does this equation work? Lagrange claimed that the first derivative with respect to time of the partial of L with respect to x dot minus the partial derivative of L with respect to x is equal to 0. Why can he say that? Well, actually, you'd be surprised what that equation really is when you transform it. And that's what we're going to do. We're going to transform this equation so you can understand why it works and what it looks like. Well, first of all, let's take the partial of L with respect to x, and we can do that here, the partial of L with respect to x. This means that only x is a variable, everything else is not a variable. That means this first term can be considered a constant. The partial of that is equal to 0. And here, that's the only variable right here. So this would then be equal to minus m times g. If we now take the partial derivative of L with respect to x dot, the partial of L with respect to x dot, in other words, the partial of the Lagrangian with respect to velocity, that is equal to, here the exponent comes down, 2 times 1/2 is 1, times m x dot to the first power minus 0. I just write it there so you can see that we're not ignoring that. That actually is 0 when we take the partial derivative of this with respect to x dot, since there's no x dot in there. And then if we take the first derivative with respect to time of this, we can then say that the ddt of the partial of L with respect to x dot is the same as the first derivative with respect to time of mx dot. And of course, the derivative of this with respect to time gives you the second derivative, which is x double dot. So this is equal to m times x double dot. Now, let's try to make sense out of this equation. We'll substitute those things back in here. And so this becomes equal to m times x double dot minus the partial of L with respect to x, which was equal to a minus mg. So that's equal to a minus mg, and that is equal to 0. Now what we're going to do is we're going to move this to the other side. So minus times the minus becomes a plus, so we have mx double dot plus mg is equal to 0. Move that to the other side, we get mx double dot is equal to minus mg, and now I'm going to turn the equation around. There's a reason for that. So we can write that mg minus mg is equal to mx double dot. Now you'll be surprised what that equation really will tell us. Mg is the weight of the object. The weight of the object, so let's use a different color here. So in other words, the Earth pulls on this object with a force equal to mg, and since the direction of the force is downward, it's a negative mg. It's equal to the force of gravity pulling the object down. So this is, in essence, the force pulling on the object, so this can simply be replaced by the force. Equals m is simply the mass of the object, and x double dot, what is x double dot? Well, that is equal to the acceleration of the object, which of course will be in a negative direction, so F equals ma. In other words, the Lagrangian equation, the first derivative with respect to time of the partial of L with respect to x dot minus the partial of L with respect to x equals 0, this equation is nothing more than F equals ma. The difference is that we're able to express the motion of the object in terms of its kinetic and potential energy. Oh, where am I? Kinetic and potential energy. And then by setting it into the equation like this, we can now derive all the equations of motion simply determined by the kinetic and potential energy rather than by the interaction of the equations of kinematics, which can be much more difficult in more complicated situations. So in other words, when you see this equation, all you really have to think about is that it means F equals ma. Quite amazing, isn't it, that he was able to take this equation and turn it into this, because this is much easier to work with and much more complicated situations, and I'll show you all kinds of examples. Of course, first what we should do is show you some simple examples and then slowly build up, because there's a lot of mathematics, a lot of algebra, arithmetic, and differential equations that we have to read through, wade through, so to speak, but that's really what it means, and that's why we can use it. Now you know what the Lagrangian is and why it works.